So this is the first of a series of videos on algebraic topology. I'm just going to get right into it and start proving things that we need. And this video is going to be a review of some basic things from topology. Okay, so some things. Point set topology. That we're going to need. All right. So, all right. So let's start with the theorem. So theorem. Okay. So it has two parts. So the first part says that if X is a compact Hausdorff space, Hausdorff space, and Y is Hausdorff, then F from X to Y is closed. Okay? And a consequence of this is the following. The following is that if F, as above, is a bijection, then it is a homeomorphism. So okay, so this is one of the weird things about topological spaces that if you have a continuous bijection, it is not necessarily true that the continuous bijection is a homeomorphism. A homeomorphism is an isomorphism in the category of topological spaces. It means that it's a continuous map, it's bijective, and it has a continuous inverse. Okay? So let's kind of recall what some of these words mean. So the word compact, right? So compact means for every open, it has the Hein-Borel property. So compact. So this is the Hein-Borel property. So every open cover has a finite subcover, right? So it has a finite subcover. Okay. What's another word that we need to define? So closed map. What does closed map mean? So a continuous map of topological spaces is closed if the image of every closed set is closed. So not every map is closed. And I believe that's equivalent to open. And then, an open map would be one where the image of every open set is open, right? So we know by the definition of continuity, or the definition of a map of topological spaces, so a topological space is a set with a collection of distinguished subsets which are called open. And the map is called continuous as the inverse image of every open set is open. Okay, and so sometimes we want the image of an open set to be open, and that's an open map, or sometimes we want the image of a closed set to be closed. So it's also equivalent to be continuous as if the inverse of a closed set is closed. Okay, the inverse image of a closed set is closed. And then Hausdorff, what does Hausdorff mean? So Hausdorff. So I'm going to try and obey this new rule that I read on Twitter, which was that if you're going to have, so you should, if names are used as adjectives, right, then they should be lowercase, which I think is actually a really great rule. Okay, so in that case, maybe I should do this. Okay, so it should be a lowercase h. All right, so okay, so what does Hausdorff mean? So I can draw the picture. So it says that if you have 2 points in the set, A and B, they can be separated by 2 open sets, right? So any distinct points can be separated by a disjoint opens. So disjoint open sets. Okay, so now we have the meaning of this, and now we can go into the proof. And so the proof is going to use like 3 lemmas, and it's going to be a really great review of all the topology that we're going to need. Okay, so here's the proof of the theorem. Okay, so the proof of the theorem it goes as following. Okay, so we take, so let A be a subset of X, let this be closed. Okay, so since X is compact, this implies that A is compact. So that's fact 1 that we're going to need, is that closed subsets of compact sets are compact. Okay, so this is fact 1. Okay, all right. So the other thing that we're going to need is that so since the so we're gonna have that the image of this thing is compact. So since the continuous image of a compact set is compact, f of A is compact. This is property 2 that we're going to need. And then, so the last thing that we're going to need is that compact subsets of Hausdorff spaces are closed. Since compact subsets of Hausdorff, let me move this up a little bit. Of Hausdorff spaces are compact, are closed. So this implies that f of A is closed. So that we showed that the image of a closed set A is closed. F of A is closed. Okay, and so now if we have a bijection, okay, so now this is what I was saying, is that if you have a bijection, which is so we want something which is a bijection. So now I can prove 2. Right, so this proves 1, and so now we have that. So we have that this map is closed, right? And so if you have a bijection, it's automatically a closed map. So that means that the image of an open set is open, right? And that that makes the inverse map continuous. Okay. So that's how you prove that it's a homeomorphism, is not only that you have the inverse, but the inverse is also continuous, which is forced by this open mapping property, or closed mapping property. All right. Okay, so let's go. So we had those 3 things. So we had 1, 2, 3. All right, and so now let's kind of, I just want to go over these to review a lot of the point set topology that that's kind of a prerequisite for this course. Okay, so let's just go at it. Okay, so all right, so let's do the first property. Okay, so the lemmas here. So the lemma 1. Right. So what did lemma 1 say? So lemma 1 said that closed subsets of compact sets are compact. So closed subsets of compact sets are compact. All right. So that's our first property. So let me refocus there. Okay. It's a little blurry. There we go. Okay, so closed subsets of compact sets are compact. Okay, so let's do a proof. All right. So suppose. So let's let a subset of X, so X is compact, be closed. All right. So then what we're going to do is we're going to write A as the so let's say it's contained in the union I and I of UIs. Okay, so and then okay, we could have written UI with UI intersect A, because that's what the subspace topology is. It's these things, and so this would be a cover of this thing by opens, but it suffices to just talk about it like this. Okay, and so this is some arbitrary index set here. So this is a subspace. So this is the subspace topology that I want to remind you of. Okay, so okay, and so we're going to take a cover, and so without loss of generality, let's assume that X is equal to the union of I and L of I's of UIs. Okay. So if not, we can just extend. We can make this thing a little bit bigger. Okay. So by compactness, of X, right? Well, X is equal to the union of I is equal to 1 up to n of UIs, right? And this implies, hence, that A is equal to the union from I is equal to 1 up to n of UI intersect A. So here, okay, so notice here I changed my index set from like some arbitrary set to just the integers between 1 and n, and that's something that I'm going to do frequently. I'm just going to relabel the n of these that appeared like this. Okay? So then we have this, and this is this proves the result. All right. Okay, so let's prove the next result. So the next lemma was that. Okay, so the next lemma was that the continuous image of a compact set was compact. So the continuous image of a compact set is compact. All right, so let's do the proof. All right, so if f from x to y, so this is a continuous map, so a morphism in the category of topological spaces, and A here is compact. So what we're going to do is we're going to let we're going to cover the image. Consider a union of open sets in the target, right, that contain this thing. So let's just cover this by open sets. Okay, so these are open sets in Y. Okay, so all right, so by continuity, the inverse image of these open sets are open. Right, that we have that A is contained in the union for I and I of F inverse of VI. Okay, but by compactness, we can change this to a finite union. So by compactness, so we can change this to a finite union. We have the union from I is 1 up to n of VI, and this contains F of A. All right, so there's a subcover like this. Oh, sorry. I skipped a step here. Well, by compactness we have. Sorry. Let me just continue on the next page. So by compactness we actually have. what do we have? So we have that this union here. This is why I like the dockhand, because I can just do this. Okay, we have this union here, right? Can be replaced by another union. So by compactness, it can be replaced by a finite union, vi, from I is equal to 1 up to n. So I'm doing the thing where I'm replacing that arbitrary index set by one's indexed by n, and I'm pretending like I was in both of them. Okay, this thing contains A, right? And so now we can take the image of this, and so this implies that the union from I is equal to 1 up to n of v of I, right? This thing contains A, or f of A. Okay, so what we did was we started with, so here what we did is we started with, so let me just try and refresh that all the time. So we started with this f of A, and we started with an arbitrary cover, right? And then we showed that we could reduce it to a finite subcover here. And so that shows that it's compact. Okay? So the image of a compact set is compact. All right. So now let's do the next part. Okay, so lemma 3 says the following. All right, so lemma 3 says that compact subsets of Hausdorff spaces are closed. So you can have a compact subset of Hausdorff spaces are closed. Okay, so let's just run through this now. So, all right, so let's do the proof of lemma 3 over here. We have lots of space, so. All right, so we have this statement here that we're going to try and prove. All right, hopefully this is kind of an experiment to see how small this goes, but I think it'll be okay on YouTube. Maybe I'll have to write a lot bigger. We'll see. We'll see what happens. Okay, so all right, so let's do the proof. So so we're going to let the following happen. So X be a Hausdorff topological space. Okay, so we're going to let A in X be compact. So this doesn't necessarily have to be closed. It's just some random set which has the Hein-Borel property that if you have an open cover, then there's a finite subcover. Okay? Sometimes it's called quasi-compact in other spaces, but for this class we're going to follow like the Munker's terminology and we're going to do this. So so here's what we need to do. We need to show that this is closed, and so that means that we need to show that the complement is open. So AC is the complement of X set minus A. Okay, so here's the picture. The picture is here is X, right? Then here is A, and here is B, right? And what we need to do is we need to show that the complement of this is open. So we need to show that there's some U. So we need to show some U, or let's see what I call it later. I call it V containing B, where V intersect A is empty. And this is open here. Okay, so this is what we need to do. All right, so let's proceed. So, and we're going to try and use all the hypotheses. So here we're going to try and use that A is compact, that these are Hausdorff, that the 2 points can be separated by little disks, and yeah, and I think that's the two things that we really just need to use. Okay, so so here's the statement. So for this fixed B, for each A in A, right, there exists some UA open containing A, and VA containing B open, such that UA intersect VA is the empty set. Okay, So that's the definition of Hausdorff, right? That these two things don't that you can find. So I put an A here, and then you can find another open here and an open here, so that they don't intersect. Okay. All right. So now we'll note that here, this set here, the union for A in A of UA, if we take all of these UAs, right? So this is a cover of A. And so by compactness, we can there's a finite subcover, right? I is equal to 1 up to n, and then we can say U of AI. So this thing here also contains A. Okay? So we have this finite subcover. All right? And so now what I'm going to do, so for each of these AIs, we also have a VI where it's disjoint. So here is like, if this is A, this could be maybe like VA, and this could be UA here. Okay? So, all right. So here's what we're going to do. So what we're going to do is we're going to let U be the union of these guys. So I is equal to 1 up to n of U of AI. And then we're going to take V to be the intersection of the V's. AI. All right? And so this is a neighborhood. So since it's a finite intersection of open sets, right? It is an open set by the axioms of a topological space, right? And we also have that. So we have that their intersection is empty, right? And that's because this thing is the intersection of this with each one of those little guys here is empty, since for the AIs. The UI intersect U of AI intersect V of AI is empty. Okay? And so since V is open and contained in AC, this proves that there exists some open containing V, containing B. Let me continue this up here. In the complement of A. And since B was arbitrary, this implies that this means that AC was open, and then this means that A is closed, which is what we wanted to show. We wanted to show that that compact automatically implied closed. Let's see, where are we? Yeah, that's not, is that the, yeah, that's what we wanted to do. We were proving this lemma here, that compact subsets of Hausdorff spaces are closed. Okay, so I am going to stop here, and then I'm going to make another video on balls in their different forms in Euclidean space, because we're going to need to talk about intervals and balls a lot, and that's one of the things we'll need to handle. After that, I'm going to have to take a little detour to talk about category theory a little bit before I get into what's called the compact open topology and things like this. Okay, so all right, so that's the end of this one.